So, in this class we will discuss the wave equations for electromagnetic waves and their solutions. The content of this discussion is like this: the solution in the Cartesian coordinate system, which will give rise to the plane waves, or speaking otherwise, that a plane wave satisfies the Cartesian system of coordinates. The solution in spherical coordinates, which will give rise to spherical waves, and the solution in cylindrical coordinate systems, which will give out cylindrical waves. So, these are the main three categories of electromagnetic waves, which are the direct outcome of the solutions of the Maxwell's equation, the wave equation. You may recall that if you have a point source, then immediately around this point source there are spherical waves, but as you move away from these spherical waves, the curvature becomes less and less and you end up with a plane wave. But this, if the source is a line source, then the waves, corresponding waves which will come out from the source will be cylindrical waves. So, these three different kinds of waves we will try to analytically solve, starting from the wave equation, and we will also look at the properties. So, the pair of wave equations in free space is represented by an electric field equation and a magnetic field B vector equation, where C is the velocity of the electromagnetic waves in free space. Now, from this set of two equations, as we have seen earlier, that it can be put into a general and compact form using psi, where this psi represents E or B fields or any of the components. So, it could be a vector wave equation or it could be a scalar wave equation. This equation, when we solve that, then we will see that if we solve it in the Cartesian coordinate systems, we will find that it will give a solution which is a plane wave, and when we solve this equation in the spherical polar coordinates, then the resulting wave will be a spherical wave. In the same way, if we solve it for cylindrical coordinate system, the waves will be cylindrical waves. These are very basic and very fundamental, and it is important to know the behavior of the waves. Therefore, for a plane wave solution, we start with the Cartesian system of coordinates. As I have mentioned that electromagnetic wave at a large distance from the source becomes almost a plane wave. So, in Cartesian coordinate system, as you know, we are very familiar that a point is represented by three components x, y and z. So, in this system, the Laplacian is represented by del square del x square, del square del y square plus del square del z square. So, in this Cartesian coordinate system, we can write the wave equation in this form, that the three components equal to 1 by c square and the time derivative, double derivative of time. So, for such equation, it is well known that the separation of variables should be applicable to find out the solutions. So, expressing this psi, which is a function of x, y and z and t, for this case, we can write this psi of x, y, z and t as psi of psi, x of x, y of y, z of z and t of t, because these are the four independent variables associated with this equation. Now, if I substitute psi by this x, y, z and t, then the first quantity will give you del square x by del x square multiplied by this quantity. In the same way, the second quantity will give you del square capital Y by del y square multiplied by the other three quantities, and so on. For this quantity, this will be del square capital T by del t square into 1 by c square multiplied by the 3 x, y, z parameters. And now, if you divide that equation, if you divide the equation where you have already substituted this value by psi, that is by x, y and z, then the equation will take the form of this, that is 1 by x del square x by del x square and so on. You can see that the variables are now separated out. Each variable term is now independent, they are not connected, they are not coupled with any of the other. So, if it is so, each of the terms are independent, then they must be equal to a constant. Putting that constant for each of them, this I put equal to minus k x square, this one equal to minus k y square. You can see here I can put this minus k x square, k y square, k z square, and for this I use minus omega square, where this, then if you put it back minus k x square, minus k y square, minus k z square equal to minus omega square into by c square. So, that is what appears here. So, omega square by c square equal to this, but this is equal to k. So, the solutions of each of this equation, is of this form: x equal to this, y equal to e to the power of plus minus I k y y, and similarly z equal to e to the power of plus minus I k z z, and the time part will become t of t equal to e to the power of plus minus I omega t. So, the total solution is, now we have started from this equation. So, I put them back, I get that A is a constant, and then you multiply these three quantities which will appear in this form, and this is the plane wave solution. So, starting with the Cartesian coordinate system for the Laplacian, we end up with the solution of psi, because psi represents the electromagnetic waves, the E vector or any of the components of E, the V vector or any of the components of B. In general, each component will satisfy this plane wave equation. Now, a plane wave is usually written in this form, and if you write this, this is the compact form using this R. So, if you decompose this R, k dot R as k x x plus k y y plus k z z, then this quantity represents the phase of the electromagnetic wave. Now, if you look at the definition of a plane wave, a wave whose phase is constant over a plane surface at any instant of time is a plane wave. So, to look for that, I have this phase which is this quantity, and now that has to be constant. So, we look for the locus where this phase remains constant. Now, because at a given time we look for this phase constant phase plane. So, this omega t is a constant. As a result, this quantity is also constant. This is the well known equation of a plane. If you write in the form of the direction cosines, then x by L, y by m and z by n equal to constant, where this L, m and n are represented by 1 by k x, 1 by k y and so on. So, these are the direction cosines of. So, the reciprocal of the components of the propagation vector represents the direction cosine for the plane electromagnetic waves. So, electromagnetic waves, as you see that the phase remains constant over a particular plane. These are the periods over which the phase remains constant. This is the propagation of, so pictorially. A travelling 3-dimensional plane wave is represented by this. We have seen this. Now, if I look at the wave very explicitly, E vector will be represented by I E x, j E y, k E z, and similarly B vector will be represented by this. But each of the components E x, E y and E z will satisfy the plane wave solution. So, I can write this equation in this form. For E y I can write in this form, and similarly for E z I can write this form, and for B x, B y, B z I also get these expressions. Now, we look for the solution of the 3-dimensional wave equation for the spherical wave solution in spherical polar coordinates. Waves from a point source is the spherical wave source. We look at the spherical polar coordinate system. You have r, theta is the inclination and phi is the azimuth, r is the radius. So, any point P is represented in the spherical system in this way. In spherical coordinates, the Laplacian can be written in this form, where r is the radius vector, theta is the inclination and phi is the azimuth angle. So, look at this. This part is purely the radial part and this part represents the angular part. So, for a wave which is spherically symmetric, that is there is no dependence on the angular part, we can remove these three terms from the Laplacian. So, the Laplacian simplifies to this form, that is del square del r square plus 2 upon r del del r. We will use this reduced Laplacian to solve the wave equation in the spherical geometry. So, the Laplacian reduces to this form, which can be written in this form also by doing that manipulation. Therefore, the wave equation becomes 1 upon r del square r psi del r square equal to 1 by v square del square psi del t square, where v is the velocity of the electromagnetic wave. So, this equation becomes, using this, we can write this equation in this form. So, this is the reduced wave equation for in the spherical coordinates for the electromagnetic waves. Now, I use this equation. For that we choose a function r into psi equal to u, which is also a function of r. Then if I substitute into this equation, it becomes del square u by del r square and 1 by u square del square u by del t square. Look at this equation, this is only the function of r, this is function of time. So, where r in psi equal to u satisfies one dimensional equation. So, this represents an one dimensional wave equation. The one dimensional wave equation, this yields the plane wave solution for the transformed function this. So, by doing this through this route we get a plane wave solution, but if we, so the plane wave solution will have a form like this u r of this, where r minus v t plus g of r plus v t. So, the solution for psi is like this, but this is now the spherical wave solution. So, the solution of the above equation is thus r into psi will become like this, and hence the solution for psi takes the form of psi of r t equal to a by r e to the power of I k r minus omega t. You can see that if you are far away from the source, then the intensity, which is the mod of this function, falls by r square, and hence the amplitude falls by 1 upon r. So, this is consistent and this represents the spherical wave. There is, so for a spherical wave we write psi of r t equal to this. Now, let us check that the phase of the electromagnetic waves is a constant over a spherical surface. So, k is now the mod of k and r is the magnitude of r. A wave having the same phase over a constant spherical surface at any instant of time will represent a spherical wave. So, because it is constant at a given time, therefore, we set omega into t is also a constant. Therefore, k into under root of x square plus y square plus z square, which is the mod value of this r vector, is equal to constant at a given time. Therefore, if you square both sides, we get x square plus y square plus z square equal to constant, and this is the equation of a sphere. So, all this is very consistent. Alternatively, there is an alternative way of arriving at the spherical wave solution. The Laplacian reduced form of the Laplacian you have seen like this, which can be reorganized into this form, and then the wave equation becomes like this 1 by r square del del r of r square del psi del r, which is equal to 1 by v square del square psi del t square. Now, we will solve this wave equation to get the. So, in this case we put, okay, there is one step that let us put psi of r equal to u of r by r. So, the equation del psi del r now becomes 1 by r del u del r minus u by r square, just del del r. If you do of this, you will get this equation. Now, this equation will give you, when multiplied by r, you get r square del psi del r equal to r del u del r minus u. Hence, del del r of r square del psi del r is equal to this, which will give you two terms which are identical, but opposite in sign. So, they will cancel, these two terms will cancel. So, this left hand side now becomes r del 2 u by del r square, del 2 u by del r square, this quantity, and the wave equation now transforms to this form. So, because 1 by r cancels from either side. So, this is again a well known equation, and we can use the separation of variables, because r is a representation for the radial function and t is for the time part. So, if I substitute this u equal to r of r and t of t into this equation, then we will get this, there will be t multiplied by this and r multiplied by this. Now, if you divide both sides by r and t, I get this equation. Now, each term is independent and they must be constant. So, using the same approach, we can write each of them is equal to minus k square. So, the solutions are now this equal to minus k square. This equation is again a well known equation whose solution is r of r equal to e to the power of plus minus I k r, and t this equal to minus k square will give a solution which is e to the power of plus minus I omega t, where I have used this omega equal to k into v, the frequency of the wave. So, the total solution takes the form of u of r equal to e to the power of I k r plus minus omega t. But we started with psi. So, to get back with a with an equation of psi, we should write psi of r equal to 1 by r e to the power of. So, again we end up with the spherical wave, and the general solution of this wave is psi of r 1 by r e to the power of I k r minus omega t plus e to the power of, this should be plus. So, this is spherically outgoing waves, and if you put a plus here, this should be spherically incoming wave. A travelling spherical waves, you have a source. If you move radially outwards, then they will form the wave front which are the surface of the spheres. So, at a distance r, the phases will be constant, at a distance 2 r, the phases are constant, and so on. Now, we will look at the cylindrical wave. Cylindrical wave is realized from a line source. If you have a linear chain of radiating dipoles or linear chain of radiating system, then all around the line in a cylindrical surface, the phases will be constant. So, look at this cylindrical coordinates. If I have my source sitting here, then on the surface of the cylinder, the phases will be constant. The representation is, this is the azimuth phi, this distance, this is rho, and the height is z, which is the usual notation for cylindrical coordinate system. So, the Laplacian in cylindrical coordinate system comes through this equation for psi. So, del square psi will be involving del square del rho square 1 by rho del rho and the azimuth part. The Laplacian in the wave equation, this Laplacian gives you the wave equation in this form. With the angular and azimuthal symmetry, that is, if I assume that it is independent of the azimuthal symmetry, we can write this equation only as a function of rho, and the wave equation takes the form of this, because you can remove these two terms because of the independent azimuthal symmetry. The solutions of this wave equation, the solutions of this equation are well known Bessel functions and can be represented by this, where this Bessel function has the argument of this propagation constant and the radial coordinate rho times the e to the power of I omega t. For large distances, rho, these cylindrical waves are approximated as psi of rho t is equal to this. So, 1 upon under root of rho, this is again very consistent. A travelling spherical waves look like this. You have a line source, there is a cylindrical surface with constant phase. At some larger distance, the phases are constant over a cylindrical surface, and so on and so forth. So, by doing this, we have discussed different types of waves, particularly the spherical wave, the planar wave and cylindrical waves, which we have solved from starting from the Maxwell's equation and the wave equation.